Hello and welcome to Physical Attraction, where we're going to be continuing our series on negative emissions technologies with this, episode 9, The Ocean Green. Just on occasion, you hear a real-life historical quote which sounds like it could have easily come from a diabolical Bond villain. So it is in this case with the following remark. Give me a half-tanker of iron, and I will give you a new ice age. No, this wasn't said by Blofeld or Hank Scorpio. Instead it was said by John Martin, an oceanographer from the Moss Landing Marine Laboratories. To understand how these things, a tanker of iron and a new ice age, can be related, and why it is that this has been linked to climate change, we need to return to the sketch of the carbon cycle that we talked about earlier in this series. These are the sort of long-term processes that take CO2 out of the atmosphere and move it between different reservoirs, including the deep ocean. We mentioned in that one of the processes that gradually removes CO2 from the atmosphere and stabilises its concentration is phytoplankton in the oceans. Some of these plankton, specifically the diatoms, generate shells made of silicon carbonate. When they do that, they affix CO2 into these shells in the process. And then when they die, some of these shells sink to the ocean floor and sequester some of the carbon in the deep ocean, isolating it from the atmosphere in exchange with the atmosphere for centuries in deep ocean currents. Martin was studying the phytoplankton in the oceans, attempting to resolve something of a mystery. In some regions, these algae and plankton would bloom dramatically, with large quantities of algae and plankton erupting on the ocean surface. In other regions, though small numbers of plankton did seem to be present in the water, no bloom could be seen at all. The traditional explanation amongst oceanographers at the time for these desolate zones in the ocean, where no blooms were seen, was that perhaps there were just too many of the plankton's predators. So these diatoms can't bloom because there's a thing called zooplankton which eat these blooms, and they might be prevalent in these particular waters which prevent the blooms from getting out of control, but once you're past a threshold, perhaps you can see these blooms where there aren't many predators around. But Martin had a different explanation. He had studied the concentration of various nutrients in the ocean. These dead zones had plenty of sunlight and other nutrients which would typically be required for plankton to grow, but they were missing one thing. He suggested that these waters might simply be deficient in one key nutrient, which prevented the blooms that were seen elsewhere. And that nutrient would be iron. Martin had another hypothesis too, that this process might be one of the long-term processes that help to regulate the Earth's climate over the course of decades and centuries. In prior ice ages, large ice sheets trapped water on continents, which means that overall the precipitation would end up being much lower because you have less water that's being evaporated out around the place, and in a colder climate you'd have less precipitation as well. So this actually meant that in prior ice ages, although you had an icier Earth, you also had a drier and dustier Earth. You have these deserts to consider that would be in place of the liquid ecosystems that we see today. You would have winds that would blow dust and rust containing iron onto the oceans. Could it be that ice ages were in part stabilised by this process? A constant supply of iron-rich dust might allow the plankton blooms to continue in places where they would not otherwise be favoured, thus drawing down CO2 from the atmosphere more rapidly and maintaining the concentration at a lower, colder level, helping to stabilise the climate in one of these ice ages. Martin was convinced that iron was the main point to these algal blooms appearing in some places and not others, and he was even able to conduct a test of his experiment. One of the regions that was lacking in iron, but potentially otherwise good for plankton, was the Southern Ocean. That's the ocean that encircles Antarctica. In 1989, Martin went there and simply filled some plastic bottles with plankton and seawater. It was really a classic experiment of the kind you might even do in school. Some bottles have iron added to them, while the others are left alone. The results seemed to confirm Martin's theory. The bottles with the iron quickly became clouded with plankton, while the bottles that had none remained more or less the same. It appeared from this, then, that iron deficiency was a limiting factor in the production of these plankton in the Southern Ocean. This was 1989, and around this time, of course, the threat of anthropogenic climate change was first coming into mainstream public acceptance. This experiment, after all, took place just a year after Jim Hansen's testimony to the US Congress, which introduced the term global warming to the popular vocabulary, although scientists had of course been investigating the possibility that human-made CO2 would cause warming for much longer than that. So naturally, the next thought that everyone came up with was whether we could use this phenomenon to try to offset the human-induced CO2. This idea has become known as ocean iron fertilization, And the idea is pretty simple. You would put iron into these places where the plankton wouldn't bloom. You would provoke a much bigger plankton bloom than normal, and this would hopefully lead to more CO2 being sequestered by these plankton and therefore sucked out of the atmosphere. Despite his flippant remarks we quoted at the top of the episode, Martin was, like many scientists who have considered these concepts over the years, somewhat reluctant to intervene in the climate system in this way. I quote here from Caroline Doppierer's excellent article, The Iron Hypothesis, which deals with Martin's life and times. He said, quote, "I will never advocate shooting from the hip iron fertilization without the detailed research to understand it," Martin wrote to one worried critic. "But adding a little iron to the ocean would be a lot better than allowing the climate to heat up," he said. He said, quote, "I agree that the ideal would be to have the average American get out of his car, have the Chinese not develop their coal resources, have the Brazilians not cut down the rainforest," he wrote. However, we don't live in an ideal world. Martin didn't live to see the first large-scale experiments to see if this could work as a way to combat climate change. He died prematurely in 1993, shortly before the first such expedition was due to take place. But his hypothesis, and that strange promise that a tanker full of iron could be enough to change the Earth's climate, has led to decades of study and debate. You can see why, as climate engineering schemes go, this one is potentially so attractive. In purely theoretical terms, it's actually something of a dream. You have potentially a very high leverage intervention that you can make. It's going to enhance a natural carbon sink that you already know works, that can store CO2 in the long term. And it might be that you might not actually have to do all that much to get a big effect. Those of you who listened to our episode on enhanced weathering will remember that we talked about how you would have olivine that you would crush up, and this would react with CO2 to store it more permanently. But part of the problem with that is that the chemical reaction there is 1-to-1. So you would need to mine a ton of olivine or so and grind it up to extract a ton of CO2 from the atmosphere. And that obviously means that to extract billions of tons of CO2 from the atmosphere, you're going to need billions of tons of olivine. So it's a huge undertaking to actually get this to work at scale. Part of this is just the inevitable problem that we've talked about so many times in these episodes about how difficult it is to do things on the scale of moving billions of tons of CO2 around the place. And that never really goes away. But if you look at phytoplankton shells, the ratio of iron to carbon atoms is 106,000 to 1. In other words, assuming that all of the iron that you're using is going to end up being converted into these shells, the theoretical maximum here is that you might be affixing 106 tons of carbon for every kilogram of iron that ends up in these plankton shells. Unlike other methods, you have these phytoplankton, which are, after all, solar-powered, through photosynthesis, doing all the work for you to affix this carbon dioxide. And the location is good too. Everything can be tucked away in the Southern Ocean, where it will have minimal impact on ecosystems that humans really care about. This is sort of the dream of a very slight intervention which just nudges these algal blooms into action. All you'd have to do is dump the iron into these regions with a fleet of ships, and then these big algal blooms will act like a big carbon sink that can provide you negative emissions at scale. Of course, you can argue endlessly about the potential impacts that creating these big algal blooms would have on the environment, but I do think that part of this fact that it would be in the Southern Ocean around Antarctica means that, at the very least politically, it might be less controversial than other means of trying to do something like this. It's different to spraying dust over all of the crops that we have and all this kind of thing, because there's actually going to be fewer people who are particularly concerned what happens in the Southern Ocean. Whether that's right or wrong is something that we can all debate. So various people have, of course, since this was first proposed, tried to quantify both the scale and the price of doing this to compare it to other forms of negative emissions. Unfortunately, it turns out that doing this is extremely difficult because of large uncertainties that are involved in this process. Some of the earlier estimates, which I'll provide for scale, although I think they look quite optimistic given what we know now, suggested that this method might be able to sequester CO2 for less than $10 a tonne, and that it could potentially sequester billions of tons of CO2 all told, making a significant dent in our global current carbon emissions each year. One point to make, of course, is, given where we are now with climate change, this is all a far cry from the tanker full of iron for a new ice age promises. At best, even if this worked to its absolute maximum expected potential, we wouldn't expect it to be able to do too much more than offset a fraction of our present-day emissions with this method. For example, there was a famous paper, it's quite old now, it came out in 2009, but by Lenton and Vaughan, which overviewed a lot of these different options. And they tried to compare them using this one metric of radiative forcing. So this paper was the radiative forcing potential of different climate geoengineering options. And basically what they looked at there was the potential to offset human influence on the climate through a variety of different methods, ranging from cloud seeding and painting roofs white all the way through to large-scale afforestation and iron fertilization in the oceans. And they suggested that the maximum radiative forcing that such an iron fertilization method could cancel out would be around 0.3 watts per square metre. Now I know that typically in this series we've tended to talk in terms of billions of tonnes or gigatons of carbon, and not radiative forcing equivalents. But to give you a sense of scale, it might help to think back to earlier in the Climate 201 series and remember those climate change scenarios. So you remember that there are all these climate change scenarios, these RCPs, and RCP 2.6 is the one that stays below 2 degrees Celsius. RCP 4.5 is the middle of the road climate change scenario where we warm between 2 to 3 degrees Celsius by the end of the century. And RCP 8.5 is the insane hellscape where all of the truly awful stuff happens, which, we hope now, thanks to our efforts to make clean energy cheaper and focus on climate change rather than just burning fossil fuels like there's no tomorrow, probably won't happen. But the reason I mention these is that those numbers refer to the radiative forcing at the end of the century due to humans in watts per square metre. So you can now get a sense of comparison for what we're talking about with this Lenton estimate for ocean iron fertilisation. They're saying that this technique could perhaps cancel 0.3 watts per square metre, compared to 2.6 in the mitigation scenario at the end of the century. So it probably works out to being around a couple of tenths of a degree. Alternatively, the most recent IPCC report at the time of writing estimated that in 2011 we had inflicted around 2.3 watts per square metre of forcing onto the planet net. That's the net effect of all human activities. So greenhouse gases, minus aerosol cooling and all that sort of thing. So again, 0.3 would be cancelling maybe an eighth of the climate forcing that we've currently imposed on the planet. So at least according to Lenton's estimate, it's not exactly a new ice age, but it certainly would help. In some ways, it's not a terrible thing, because obviously I think the first question people always have when you talk about these geoengineering scenarios is, what if you go too far the other way? What if you accidentally set off some insane algal bloom chain reaction and the whole ocean becomes choked with algae, and then we'd end up with a day after tomorrow type scenario where we get rapid cooling or set off a new ice age by accident. Scientists really aren't concerned that this would happen, no matter how much you try to fertilise the Southern Ocean, because even the maximum effect is likely quite small compared to the total anthropogenic effect of greenhouse gas emissions. However, those of you who have listened to the series on negative emissions so far, and thanks for sticking with it, will know that there's a but coming. And those of you who have an intuition for how systems work, especially in realms as complicated as the carbon cycle and the climate, you'll probably already see where this is going. Because the obvious point to make is that in reality it's not clear at all how much of an effect you actually have by trying to manipulate this natural system, and how effective it is really to simply dump tons of iron into the ocean and hope that plankton will do all of the rest of the work for you, and that it will result in net sequestration of CO2. The trouble is that this efficacy, how much sequestration bang you really get for your iron fertilisation buck, is subject to an awful lot of uncertainty. And a lot of this comes from the fact that the real world is much more complicated than a test tube. So that ratio is not going to play out in the real world conditions. And that's due to a lot of the complex processes that play out in the ocean when you try to do something like this. Now, the evidence surrounding this has actually been strengthened by a number of field-scale experiments which have been performed over the years. There have been at least a dozen small-scale experiments attempted so far to fertilise the ocean with iron ore over the years. On one level, these experiments do seem to have some success. The algal blooms that they do provoke does seem to be a real effect. Scientists on the boats observe changes to the colour and sometimes even the smell of the water, and large-scale pictures by satellites do seem to indicate that there's an algal bloom where there wasn't one before, specifically where the fertilisation takes place. So there's definitely iron-deficient parts of the ocean where you could dump iron and you could cause an algal bloom. But even once you have that, the question of how much carbon you're actually sequestering and how reliably you can do this, these things are still up in the air. In a laboratory beaker, you may be able to sequester 100,000 kilos of carbon for every 1 kilo of iron that goes into the shells of plankton. But the real world ain't a lab beaker, and the plankton don't get all of the iron. When you're distributing the iron into the ocean, it can sink fairly rapidly towards the ocean floor, depending on the nature of the strong and varied currents in the Southern Ocean, which distribute it around the place. Even the process of calculating how to drop your iron to spread it out over the maximum possible area is a difficult one on account of these currents. The effect on the blooms, therefore, is very sensitive to the location and the circumstance where you fertilise with this iron. In one experiment, a large bloom was suddenly subsumed by a mass of less dense water, which moved over the iron-fertilised water, dragging it down and preventing the iron from really taking effect after just 5 days of the experiment. Ocean currents are of critical importance to how this actually pans out in practice, and so quite often you will see some of these experiments will take place in the middle of a big gyre, a big sort of swirl in the ocean currents, where you can hope that there's some level of stability and the iron will stay in place for a bit so that you can monitor what's going on. But these blooms and the iron fertiliser can end up trapped in these swirls and gyres in the ocean, or they can spread out across large areas in bigger spirals, depending on where the currents take everything. Imagine trying to fertilise soil that was constantly moving and churning under your feet, and then trying to figure out where to plant the seeds, and you might begin to get the picture. Of course, alongside where the fertiliser actually goes and where the blooms end up, there are ecosystem questions too. Even assuming the iron gets to the places where you want it to, it's not like there's a simple recipe where the plankton blooms are proportional to the iron that you can add in a real ecosystem. Other limiting factors, like the availability of other nutrients, including silicon, can limit the size of the bloom once it's saturated with iron, and depending on the local content in that part of the ocean. Certain blooms might die out fairly rapidly once the proportion of phosphate in the water is depleted, so you get a sort of short, sharp bloom that is caused by this massive glut of iron, and then suddenly it just dies away again, and you don't really get that sustained uptake of carbon that you're looking for. Certain blooms might die out fairly rapidly in this case. Depending on which species are present in the water to begin with, too, the amount of carbon that's fixed by the blooms will change. Remember, we said that these diatoms are the ones that make these silicon carbonate shells, but if they're not these diatoms that fix carbonate in their shells, that are the dominant species, then you might not get as much carbon ending up at the deep ocean. There's also the zooplankton that eat the diatoms. Well, if a lot of them are present, then they can limit the population of the bloom in turn. And those of you who've dealt with predator-prey models can sort of imagine some of the cycles that you might get into, where you have loads of these predators and then they die off and then the prey come back and all this sort of thing. So it's a little bit tricky to balance that as well. Finally, the largest uncertainty is how much additional carbon sequestration you actually get from this whole process. This is, of course, a common theme amongst these processes where you have what is ultimately quite a blunt intervention, just dumping a whole load of fertiliser into a system, into a natural system that has all these complex webs of interdependency in there. It's possible to visualise the blooms in satellites, but it's a little bit harder to actually determine how much of that carbon ends up on the ocean floor, and doesn't just cycle through the system by decaying on the surface or being consumed by something else that decays on the surface, or evaporating out or whatever. It's a complicated and challenging task, and again it depends on the intricacies of the ocean currents that are difficult to model and pretty much impossible to control. And so the end result is that there's higher uncertainty around this as well. To see how all these factors interact, we can simply look at the differences between two major experiments. The European Iron Fertilization Experiment, or IFEX, in 2004, found that they were capable of producing a large bloom when they covered 167 square kilometres in a big ocean eddy. And they were able to measure that at least half of the biomass of the diatoms ended up sinking around 3 kilometres below the ocean. So in this case, you had a huge bloom, it was very concentrated, it was very large. Any decay process was just overwhelmed by the amount of algae, as were any predation processes that might be taking place. And it seems like at least half of the stuff that was produced did end up sinking to the deep ocean. So that probably did result in some net carbon sequestration. But another experiment in 2009, LOHAFEX, which was by the Indian and German governments, this dumped iron in waters that were low on silicate. The result was that there was a large bloom of some types of phytoplankton, but not many of the carbon-rich diatoms, and the plankton ended up being eaten by zooplankton anyway, with the carbon that they had secured mostly being returned to the atmosphere. This again demonstrated how site-dependent and how fiddly the effects are of trying to do this. And this, of course, further cast doubt on these idealised models where you can get 1 billion tonnes of CO2 reliably removed from the atmosphere if you fertilise these large sections of the iron-poor ocean. And this is essentially the net takeaway of experiments that have been conducted so far. There are a variety of different estimates for how effective this method might actually be. To any would-be people who are hoping to use this for negative emissions, this poses a pretty big problem. If the error bars on what you're doing are potentially going to be orders of magnitude, as they are in this case, then you can't guarantee whether you'll be able to sequester 1 billion tonnes or 10 million tonnes. And if you can't say that the cost will be, say, $10 a tonne, making it competitive or cheaper than other, arguably less controversial negative emissions methods, like afforestation, BECCS, etc., or whether it will be $1,000 a tonne, in which case it's an inexpensive and environmentally pretty unsound waste of time and money to even attempt this. So again, these things are big differences, and it's quite important to get this nailed down before you attempt this at scale or suggest that you can rely on it. Now, it's worth saying that all of these experiments have tended to be opposed by large numbers of environmentalists, and the reason why is fairly obvious. This definitely feels like intentionally tampering with nature and natural systems, because that's exactly what we would be doing, as well as dumping in our already over-polluted oceans, because that's also what we're doing. In some cases, there's been legal action taken about whether these experiments actually violate existing laws against dumping. For example, there was an extremely controversial rogue experiment undertaken in 2012 by a guy called Russ George. He was a Californian businessman who, in collaboration with a salmon fishing company, kind of went rogue and undertook his own experiment, dumping 100 tonnes of iron into the Pacific Ocean off of Canada. The primary aim was obviously not really having any impact on the climate, because that's quite a small amount of iron to do that, but perhaps restoring the salmon population there by changing the ecosystem. It appears that his actions did indeed cause a bloom of phytoplankton, although it's likely that he then exaggerated its positive effects. But having essentially done this as a rogue experiment, there were legal battles over whether he had violated the UN's Convention on Biodiversity, or the London Convention of the dumping at wasted sea through his actions. I think the legal status of unilaterally undertaking these geoengineering type experiments is still pretty much up in the air, as far as I can make out, which can lead to its own concerns, and the fact that it's still disputed under international law is one for the lawyers amongst you to work out and to investigate and research. I know there's a lot of legal scholars who have looked into things like this in the past. Not really my area, so I won't comment on it any further, but this guy was potentially in trouble with these two international treaties. And as a result of that and the criticism that his actions got, the whole thing ended up dissolving in acrimony, and the various parties ended up suing each other, and there aren't really any active attempts ongoing to repeat this particular experiment or anything like it. But I mention it just to point out that this is far from uncontroversial, and the concerns that various bright-eyed billionaires might try to unilaterally hack the planet in this way, these are definitely active concerns in the academic and political community, even if this particular experiment was a pretty small-scale event. So what can we really say about the whole idea of ocean iron fertilisation now? It's in a fairly dismal place. Occasionally some new character or scientific group comes up with a new scheme or proposal to conduct an experiment or to find out some more information about it, but in the last few years these have increasingly not got off the ground at all. Sometimes these experimenters aim to repeat what's already been done in new locations. On other occasions they feature new ideas for tinkering with the ocean's biogeochemistry. For example, some have proposed that we should be focusing on small marine organisms called salps instead. These salps, they eat plankton like diatoms, but they convert their food into carbon-rich pellets, which might sink more readily to the ocean floor, and thereby sequester carbon more efficiently. As it is, very few of these schemes are really getting off the ground at the moment, and my suspicion is that these high levels of uncertainty and the relatively low potential for this to really make an impact on climate change, alongside the obvious environmental and PR concerns with dumping metal in the ocean to achieve your objective, this probably means that ocean iron fertilisation has really had its day as an idea. I don't think it was as effective as people hoped, and I don't think it will end up being attempted at scale. The potential rewards are just too small and uncertain for the hassle, really. If, far from a new ice age, fertilising most of the ocean with a giant fleet of ships might just result in the equivalent of a 1 to 2% global reduction in emissions, it's not clear that people would necessarily bother. In that case, you might be wondering why I've dedicated an episode to the story. Of course, it's a fascinating glimpse at the Promethean idea of twisting some of the natural systems of the carbon cycle to our advantage. It's a creative idea to begin with. It's also an educational illustration of the fact that the complexity of these systems, the secondary effects, and the real lack of information and ability to predict the consequences of our actions in a way that we're confident about, really does end up making it unclear that any of our attempts would be successful in doing what we hoped. These lessons can be applied and borne in mind for other geoengineering efforts or schemes that have been proposed or continue to be proposed throughout the years. But more broadly than that, as controversial as the process has been, I also think that it's an example of where science and scientific principles have actually worked pretty well to try and tackle this type of thorny issue. The idea was suggested. Experiments were conducted to test the hypothesis. Small-scale, well-thought-out, and carefully considered field trials were considered appropriate, and by and large, with a few notable exceptions, they were conducted by careful scientists who gathered data without doing too much harm in the process. These are not simple ethical issues, but as I'm sure you will appreciate from having heard me talk about climate change so much, and how difficult it's going to be to get any solution working, there is no issue that is completely devoid of ethics. It was worth investigating to see whether there would be some very high leverage solution here, where, for a relatively small impact on the Southern Ocean, you might be able to sequester an awful lot of carbon, and thus avert an awful lot of damage to humans and other ecosystems around the world. That doesn't mean that it would be ethical to try and use this as some sort of substitute, where we have an enhanced ocean pump that makes up for human industrial civilization continuing willy-nilly, but it's the sort of thing that you would want to investigate at the very least so that you knew what you were dealing with before you figured out whether this was indeed a potential to create a new ice age. As a result of the field trials, some of our uncertainties about how successful this would be were refined, new phenomena were discovered along the way, our understanding of natural processes in the ocean has been improved and enhanced by these experiments. And the end result basically has demonstrated that you do indeed need a lot more than a tanker full of iron to produce a new ice age. At this stage, I think it's probably demonstrated to most people's satisfaction that the uncertainties and potential harm maybe from attempting this probably far outweigh the relatively small benefits of doing so, and in this sense, you feel like it's probably a bit of a dead end. But that doesn't mean that we aren't better off for the relatively minor expenditure to get the information about whether it might work and what the limiting factors may be. So I do think this is a good example of science functioning as intended to try to test and resolve an interesting, albeit controversial, hypothesis. A final note, and perhaps a pleasing link-up. In the episode we did on nature-based solutions a few ago in this series, we talked about how preserving whales has been suggested as a way to enhance the ocean sink of carbon, as they eat carbon-rich organisms in their life, and then they die and their bodies sink to the ocean floor. Some studies have suggested that the whales themselves act as marine ecosystem engineers. They defecate iron into the water, which can then feed the phytoplankton that in turn form part of their food chain in the first place. So rather than dumping masses of iron in the Southern Ocean, it may be that we can achieve some of the same benefit simply by leaving whales alone and encouraging them to thrive in the oceans once more. For the time being, though, I expect that we will probably be leaving the ocean to bloom alone. Thank you for listening to this episode of Physical Attraction. Remember, you can find us on the web at physicspodcast.com. There you will find the contact form, any comments, questions, concerns, topics you'd like me to cover, things you'd like me to explain about climate or anything else, people you'd like me to interview. Do get in touch. I really enjoy getting all of the emails that you can send to me there. You can get in touch with us as well on Twitter at physicspod, and on the website physicspodcast.com you'll find ways to support the show. There's the Patreon, patreon.com/physicalattraction. There, for a small fee, per unique bonus episode, at least that small fee, you'll be able to get access to lots of bonus episodes that have existed in the past. You'll be able to get access to early episodes that are not yet released on the mainstream of this show, and you'll be able to help support the show and help keep us going, pay for hosting costs and all that sort of thing, pay for coffee and biscuits for me, pay for some books, all that kind of thing, and hopefully you will get some value for money as well from the bonus episodes. Thank you very much to everyone who supports me and other independent podcasters and content creators. We do appreciate it. If you're not in a position to support us financially, then of course the best thing you can do is to tell other people who might be interested to listen to the show. There's an episode guide which will explain the different shows that they can listen to and the different topics that we've covered over the years. So that would be the first place to send them. Until next time then, please do